Greetings, my name is Stephen Williams. I'm with the National Air and Space Museum, and we have some meteorites for you to look at today. Have you ever been outside at night, on a nice dark night, looking up at the pretty stars, and all of a sudden it looks like one of them detaches from the heavens and streaks across the sky? Call that a falling star, a shooting star, or a meteor. But it's not really a star at all. It's really a small bit of interplanetary rock or metal that hits our atmosphere at a very high speed, and the friction from it hitting the atmosphere going very fast makes it glow with heat, just like the inside of an old-fashioned light bulb, the kind with a wire filament. And it glows brightly for a second or so, and that's why it looks like a falling star. Most of the ones that make it all the way to the ground and become meteorites are made out of rocky material, but a few percent are made out of metal. And we've got examples of some of those right here. This is a piece of meteorite that fell to Earth in 1969 in February in northern Mexico. A little town nearby named Pueblito de Allende gives this its name, the Allende meteorite. Now, some of the rocky materials that we get, in fact most of it, comes from the asteroid belt between Jupiter and Mars. And we know that because we watch the skies with automatic cameras. And when a meteor happens, it can be seen from several different places on Earth at the same time. But because it's in the sky above us and not as distant as the stars, it's really a matter of trigonometry. Two different observing stations see it against a different background of stars, and from that, trigonometry can be used to calculate its trajectory and thereby infer its origin point. But when you get to a meteorite like Allende, the story is different. This came from out past Pluto. Its chemistry is the initial chemistry of the solar system's raw materials. This is leftover debris from the formation of the solar system. It's older than the Earth itself and is as old or older than any rock I or you will ever touch. The meteorites that come from the asteroid belt were actually part of a larger body, at least perhaps, and have undergone some chemical processing, so they aren't as primitive or as original or as old as this one is. But all of them are important in helping scientists understand how our solar system formed and where this material ultimately came from. The problem with this is, when you look at the edge of it like this, this is the part that got flash fried as it came through the atmosphere. It's a thin layer of fire damaged or heat damaged rock. You can see the other areas, though, where the rock has been broken open. You can see that it doesn't look like this part at all. This is called a fusion crust, and it makes these hard to identify. If you're walking down the street and you trip over this rock right here, it looks like a lot of other rocks in the blacktop street. You'd never know to pick it up to see how special it really is. On the other hand, if you're walking down the street and you run into one of these things, we've cut it open so you can see it here, like it's metal. It rings like a bell if you hit it right. And almost all is iron, about 22% iron, and the rest is mostly a nickel called nickel. That we not find iron in together like you're probably dealing with air, a pot, or human colonial fact, or a slag or some other metal from artists. This is the from metal on Earth space. Metal from the. Let's think about nature's planet. In Earth, we get iron ground. We're at a concentrated level. In this case, that we high enough up mine with people can do that, dig it up, clean it in giant machines who's called crush it, and then use heat to milling the rock in the process called heat. That's where metal, iron, smelt. There aren't any more we get minerals or smelt, but they're out in space. Iron mill, that's where this came from. This particular one fell in Russia. In prehistoric times, it was found in a riverbed near Moscow. There were no miners, no mosses, no mills, no stuff involved. The only place you find metal like this in nature without human intervention is if this were one was part of a larger body a small planet or asteroid, one that would be big enough, hot enough, big enough inside for the metal to sink to the middle and the rock to float up on top. Kind of funny to think of metal sinking, but a rock or raft floats very well on a sea of liquid steel. So after the core formed, a process called differentiation, the metal goes to the middle, the rock comes up on top, and then it starts to slowly cool off and turn solid. Then, many years later, if it gets hit by another asteroid or small planet and broken apart, and we get a piece of the original asteroid's core, it looks like this. This is the guts of a dead asteroid. How's that for cool? And if you get a piece from the rocky upper part, it looks like a rock. Now the question is, what happens if you get a piece from the middle? And to tell that story, I've got to use some earth rocks. This one, and this one, and this one. These three rocks you might recognize. This is obsidian or volcanic glass. Native peoples made edged implements out of them quite effectively. This is a piece of granite. You're familiar with that from countertops and building stones, tombstones if you hang out in the cemetery enough. And then this is often used as cosmetics. This is a good skinned sandpaperer, if you will. This is a bit of frothy, glassy stuff called pumice. These three items don't look anything alike. They're not the same color. They're not the same density. This is particularly light. But they're identical in what they're made of. If you melt these things in an appropriate furnace, you can cool them very quickly and get this, cool them very slowly and get this. And because this behaves like a liquid and freezes so quickly, it's molecularly like a liquid, it has gases dissolved in it. In the cases where there's a lot of gas dissolved in it, and the pressure is released all at once on this stuff when it's underground, like with an earthquake and volcanic eruption, the upper part of this material froths, and if that froth freezes fast enough, you get pumice. So think of it as nature's soda. It's just as hard on your teeth, so don't try drinking it. But you've got a cola, a liquid material, with a gassed up version, a carbonated head, on top of it. Okay? Now, if the chemistry is different, well, let's keep the chemistry the same. This is granite. It's made out of the same stuff here. You can see that there are crystals of what are called minerals, subsets of this rock. One's black, one's gray, one's white, one's clear. There's probably more in there too if we look closely enough. All right? In this case, the cooling process was so long that the individual minerals had time to gather together, turn solid in large chunks that we can see. Now let's change the chemistry. This is a piece of lava rock called basalt from Hawaii, the big island on the Kona side. This was underground and then was erupted out in a volcano. You can actually see there's some gas bubble holes in it. It didn't have enough to make pumice like the other example. But what did happen here is it actually started to turn solid while it was still underground. And that means that the mineral that has the highest freezing temperature froze first. And in this case, it's a greenish material called olivine. Sometimes we find it in a big enough piece that you can cut and fasten it like in a gem. Olivine's a bad name for jewelry. So it's given the name peridot, or peridot, if you're from the American Southwest where a lot of this is mined. So think of this as you're inside the asteroid, the rocky upper part is starting to cool, and the first thing to crystallize are olivine crystals. They're heavier than the liquid they're in, so they sink down towards the interface between the metal core and the rocky mantle. So if we're very lucky, and we get a piece that is from that transition zone, it has both olivine crystals and a metal matrix that they're embedded in. And let me show you what can happen when you shine a light through this. You can see that the olivine crystals are translucent and allow light to go through. You can see the greenish yellow color and fracture damage that they've undergone. This kind of meteorite that contains both olivine and metal is called a palisite. Meteorites have two names, just like people. The first name is related to where it fell. That's why we have the Allende meteorite. This one fell in a place called Brahim and is the Brahim